All right, so previously we've talked about functions, functions of two variables, functions of three variables, and their partial derivatives. And their partial derivatives could, for example, be f of x, or f sub x, when we've referred to that as the partial derivative of f with respect to x. But f sub x and, consequentially f sub y or f sub z, well, they're all functions of two variables as well. And so we could also consider their partial derivatives as well. And we call these second partial derivatives or higher order partial derivatives. And so, for example, while we might have the partial derivative of f with respect to x, we might also have the partial derivative of f with respect to x, and then the partial derivative of that. So that's going to look something like this. And so if we rewrite it in our second terminology, we might also write it as such. Oops. We might write it as such, where this is the second partial derivative, written like that. And so that is the partial derivative of f with respect to x with respect to x. And so it's kind of got that double meaning there. If I could just break this down for you, this looks something like this. And this kind of helps explain the concept a little more. So we have the partial derivative of f with respect to x, and we're taking the partial derivative of that with respect to x. And so that is kind of the notation that we're using. Now we can also do the same thing with respect to y. For example, we can have the partial derivative of f with respect to y, the partial derivative of the partial derivative of f with respect to y, and it would be the same thing. The key thing here comes when we're trying to do the partial derivative of the partial derivative of f with respect to x with respect to y. So what that means is we might first find the partial derivative of f with respect to x and find its partial derivative with respect to y. And so what this looks notation-wise, at least, is like this. Let me decrease this line. So it's going to look something like that. And so we start off from inwards and we work our way outwards. And so inwards, we start here first at this rightmost side, and we say, okay, we're first trying to find the partial derivative of f with respect to x, and then we're going to find the partial derivative of that resulting function with respect to y. Again, in order to understand this a little bit more simply, just break this down a little bit more. We're basically trying to find we have found the partial derivative of f with respect to x. We're trying to find it with respect to y. And the same thing works vice versa. If I were switching these around, then we are instead trying to find, we've already found the partial derivative of f with respect to y, and now we're trying to find the resulting partial derivative with respect to x. And that simply works by that simply works even if we flipped around the two variables. So let me complete this. Okay. Now, one key thing here, which I'm going to leave for now, and we're going to discuss a little bit later in the video, is that we can ask for the partial derivative of f with respect to x with respect to y, for example. And like I said earlier, we start inwards and we work our way outwards. Well, I'm going to change that paradigm a little later, and we're going to see how and why we don't necessarily need to, the order doesn't really matter in which way we take our partial derivatives, but that's a discussion for later. So for now, understand that when we're talking about at least second partial derivatives, given the notation and when asked, we are first trying to find the first partial derivative, and then we're going to find a second partial derivative either with respect to x or with respect to y from the resulting function. All right, so let's go to our first example of what a higher order partial derivative question might look like. All right, this question is asking us to find all the second partial derivatives of the following function, the function being f equals e to the power of negative 2x cosine y. Okay, let's break this down. We are first trying to find the partial derivative of f with respect to x, treating y as a constant. This is pretty easy. We've done this before. So f sub x is going to be equal to, we're treating y as a constant here, e to the power of negative 2x. That stays, however, due to train rule, we're bringing down the negative 2 because the derivative of negative 2x is just negative 2. So we're bringing down the negative 2. That leaves us with negative 2 e to the power of negative 2x cosine y. Okay, let's leave that there. Okay, now we have f sub y, or the partial derivative of f with respect to y. All right, so we leave the e to the negative 2x. We're just going to leave that for now, treating that as a constant. We have the derivative of cosine y, which is negative sine y. And so what that leaves us with is negative e to the negative 2x power multiplied by sine y. Okay, we have found our first partial derivatives. We're not done yet, though, because now we have to find the second partial derivatives. So what that means is we're trying to find the partial derivative of the partial derivative of f with respect to x with respect to x. And so I'm going to use the del notation now to make it a lot easier for us to look at visually. So del squared f over del x squared. So what that's going to look like is, again, look, we're treating y over here as a constant. This cosine y over here is a constant. Yet again, what we're left with is negative 2 e to the negative 2x. Again, negative 2 is a constant. E to the negative 2x we're keeping as is. However, again, we're bringing down that negative 2 because the derivative of negative 2x is negative 2. So we multiply that out by the negative 2. We're left with 4. So it's 4 e to the negative 2x cosine y. Pretty simple, okay? Now, we're going on to finding the partial derivative of the function with respect to y now, okay? So this is going to look not as complicated as you might think, okay? We are essentially treating this whole thing as just one big constant. And what we have over here is just deriving cosine y, which is negative sine y. We already did that. And so what that leaves us with is negative sine y. The two negatives cancel each other out. And so what we're left with is 2 times e to the power of negative 2x sine y. Okay, moving on to f sub y. What we have here is we're trying to find, why don't we do the partial derivative with respect to x first. It's not as complicated as we might think. So del squared f over del y, del x del y. So what's that gonna be? Well, again, we're treating this whole thing as a constant, and so what that means is we're keeping the e to the negative 2x, however we bring down the negative 2. And so that's going to be 2 times e to the negative 2x sine y. Alright, we've done pretty good for ourselves so far. One more is going to be the second partial derivative with respect to y. And so what that's going to be is we're treating the whole x part as a constant. The derivative of sine y is just cosine y. And so what that leaves us with is negative e to the power of negative 2x cosine y. Okay, pretty cool. We've found all the second partial derivatives, and thus that is our answer. However, I would like to take note of something. And what I'd like for you guys to notice is that what we have is that both of these partial derivatives are the exact same. In fact, if you think about it, for this question at least, the partial derivative, and I'm going to use a different color here, the partial derivative of the partial derivative of f with the partial derivative of f with respect to x with respect to y is equivalent to the partial derivative of the partial derivative of x with respect to y with respect to x. And so to write this in other terms is that f sub xy is equivalent to f sub yx, and that is by no coincidence. Okay, and in fact, this has been established, long ago, and and it's been established through what is known as Clairaut's theorem. And what that basically means is that suppose we have a function f, and that's been defined and contains any given point a, b. Then what it's basically saying is that the functions, the partial derivatives x or the partial derivatives with respect to x, y are going to be equivalent to the partial derivatives with respect to yx. And what that means in layman's terms, essentially, is that order doesn't matter when you're taking partial derivatives, okay? You can take the partial derivative with respect to y first, and then you can do it with respect to x, or you can do it with respect to x first, and then with respect to y. You're going to get the same answer either way. So I kind of described what Clairaut's theorem is, technically. However, in practice, all it means is that order does not matter when you're taking a partial derivative. And so what that means for you as a student is that you want to take the easiest route possible when you're doing your partial derivatives, okay? So don't make it harder on yourself when you're doing this kind of stuff, okay? We're going to look at another problem, this time talking about strategies for Clairaut's theorem and taking partial derivatives. All right, this question is asking us to find the indicated partial derivative. And so we're basically trying to find f sub x, y, and z. Given the function, f is equal to ln, and then in parentheses, x plus y squared plus z cubed. Okay, I think we can do this. We can definitely do this. Let's start off with what I think is going to be the easiest one, which is going to be f. Okay, and I'll show you why. Because f sub x is basically going to be 1 over x plus y squared plus z cubed multiplied by the derivative of x plus y squared plus z cubed, where we're keeping y and z as constants. And so what that leaves us with is with just x. And so the derivative of x is just 1, because our constants are left out to be 0. And so we're left with the expression as it is, which is 1 over x plus y squared plus z cubed. Okay, we're already a third of the way there. Now, we need to do this for y. So let's rewrite this first of all to make it easier for us to do math on. Okay, so now I've kind of restructured this in order to instead have a negative exponent. And so now we can simply take the partial derivative with respect to y. Okay, so first things first is we're going to take down the negative and we're going to replace it with negative 2. So we have x plus z cubed, the power of negative 2. And now we're taking the partial derivative of y, the derivative of x plus y squared plus z cubed, treating treating x and z as a constant. And so when those two constants essentially become 0, the derivative of y squared is 2y, and so we're multiplying this by 2y as a result of chain rule. And so what that leaves us with in terms of a proper expression is going to be negative 2y x plus y squared plus z cubed squared. Okay. However, I would leave it over here as is, just so that we can do it easily for the third. And actually, there's a slight problem here with notation. We're finding x sub y, f sub x and then y, and so you want to have that notation clearly outlined over there. Okay, so now we're going to do f sub x, y, and z. We're almost there. So first things first, we're going to use this function because it's much easier to use. We're taking down the negative. We're treating the y over here as a constant. We're taking down the negative 2. We're putting it in the front. We're going to change this to a negative 3. So y squared plus z cubed, negative 3. We're keeping this 2y over here, but now we have to do chain rule. And we're treating x and y as constants. And so the derivative of z cubed is going to be 3z squared. Alright, and now simplifying this over to a much more easier to understand expression, what we're left with is essentially there's going to be 12y z cubed, all of that over x plus y squared plus z cubed cubed. And thus that is the indicated partial derivative that's been asked for. Okay, so you can clearly see we kind of went through whichever way is the easiest for us in terms of the student in order to answer the question. I could have very much easily gone and done z cubed or y squared first. However, that might have been harder to deal with a number of more constants than we had to. So I started off with x, y, and then z. And this is one of the examples where we can actually use x, y, and z instead of z, y, and x, and it's much easier for us to answer the question. All right. We'll look into one more example this time talking about partial differential equations. Alright, so this question is asking us to show that the following equation is a solution of the wave equation, or u sub tt is equal to a squared u sub xx. Well, first we need to discuss what is a partial differential equation. Well, we've been doing partial derivatives so far, and partial derivatives occur in partial differential equations that express certain physical laws. And so, laws in physics, in biology, in waves and motion and, diffusion, heat, all of that stuff. And so there are, various kinds of partial differential equations. You have Laplace's equations, stuff for heat and stuff like that. And so what that means for you as a student is that you're going to be asked to verify whether a given function, in this case we have u, and you're going to be asked to find whether it is actually a solution of a specific kind of partial differential equation. You'll be given that kind of partial differential equation, and you'll be asked to see whether it's a solution of that. So for this problem, we need to first find what u sub tt is and u sub xx is, and then we'll verify the solution. And so we'll start off by finding u sub t. And so in order to do that, we use power rule over here, x minus at to the power of 5, because that is a t containing term over there, and so we can use power rule. The derivative of x minus at, treating x as a constant, is going to be negative a, because we're essentially just trying to find the derivative of negative at, which is just negative a. And then we can do the same for this term over here, and so that term is going to amount to, again, we're using power rule, it's going to be 6 times x plus at to the power of 5, multiplying that out by a, because the derivative of x plus at treating x as a constant is going to be a. Okay, we're going to leave this function as is. We're going to now find the partial derivative of that function with respect to t. Again, we're using power rule, and it's going to be the same thing as we did before. And so it's going to amount to x minus at to the power of 4 now, because we're reducing that power, and then we're going to multiply this by the negative a by the derivative of x minus at, which is negative a yet again, so we're left with a squared. Okay, and that's actually very much similar to the a squared over here. Okay, and so we're going to do the same thing for the second term, and it's going to amount to the exact same thing. It's going to be 30 x plus at to the power of 4. Yet again, we're taking out an a because the derivative of x plus at, treating x as a constant, is going to be a, and so it's going to be a squared over here as well. So u sub tt is actually equal to a squared, and then in huge brackets, it's going to be 30 x minus at to the power of 4 plus 30 x plus at to the power of 4. Alright, so now as long as u sub xx equals this part of this expression, then we're in the clear. Okay, so let's try to find that. U sub x, now we're treating t as the constant, and so we're going to use the same exact methodology that we used originally. So we're going to bring down the 6 using power rule, x minus at to the power of 5 now. The derivative of x minus at treating t and a for that matter as a constant is just going to be 1, so we're going to leave the function as is, or sorry, the expression as is. We're adding that to the second term, which is going to be yet again 6 plus at now to the power of 5, because we're bringing down the 6 and reducing the power to a 5. Again, the derivative is still going to be 1 even after chain rule, and so we're going to leave the function as is. Okay, u sub xx is going to be 30 now, because we're bringing down the 5 and we're going to reduce the power to 4 as such. Again, chain rule doesn't really matter over here because the derivative of x minus at is just going to be 1, and so chain rule doesn't really matter. The function is left as it is. Same thing goes over here. We're bringing down the 5 and we're changing the power to 4, and so now we have u sub xx, and look, it's the exact same thing as that multiplier over there. Okay, and so now we can definitively say that because I'm going to highlight this over here, because this is equal to that, and we have an a squared over here, we can definitively say now that u sub tt is equal to a squared u sub xx, and that is a given. I'll be posting the PDF of this whiteboard on the description of the YouTube video. Thank you so much for watching. If you have any questions, please leave them in the comments and I'll try to respond to them. Otherwise, thank you so much for giving me the time to teach you and watch this video.